Alright, so lesson 4.4b, we learned two main things. The first being how to differentiate a definite integral, and the second being how to find the average value of a function over an interval. And so before we jump into all this, I'm going to take it a step back and show you that from now on, we can possibly see functions that contain integrals. Typically, functions are just like polynomials or trig stuff, and integrals are just something that's given to us. But now functions can contain integrals. And when functions contain integrals, there's a few things that are different that we might notice. The first one being that if you look at the bounds of this integral, the bounds are from 0 to t. Typically, with integrals, or definite integrals, we might see something like the integral from 2 to 7 of, I don't know, x squared, whatever's on the inside. The difference between these two is that the bounds on a normal definite integral are just numbers. But the bounds on our integral inside a function, they can have variables in them. So that's the first thing you notice. And another important thing to notice is that the variable, what the variable is in the bound, is a different variable than the one that's in the integral. In the bound we have a t, and in the actual integral we have an x. That's very important. Typically these variables, or these integrals I should say, are provided to you, but sometimes you might have to, with word problems, write your own integral. And when you have to write your own integral, where you have to have a variable in the bound, what you want to do is be sure that the integral in the bound, or the variable in the bound, I should say, is different than the variable that's actually in the integral. It's very important that they're different, so just keep that in mind. And now the last thing we want to notice is that this is just a function like normal. F of t equals all this. And when we're given a function, we might be asked about when the function's increasing or decreasing, or maxes and mins, or concavity and all that stuff. And to do that, we have to take the derivative. So, how would we actually derive a definite integral? And with the knowledge we know now, what we would have to do is we would have to actually take the integral, plug in our bounds and stuff, and then differentiate our result. So let's just walk through that, see how it works. So we're given the integral from 0 to t of 3x squared dx. So let's just, let's do the integral. So if we integrate 3x squared, we'll get x cubed, and then we would have to plug in our bounds. So 0 and t. So right here. So remember plugging top bound first, so that would give us t cubed, and then subtract plugging in your lower bound, which is 0, so 0 cubed. And t cubed minus 0 cubed is just t cubed, so that means f of t equals t cubed. And now, if we were to actually take the derivative now, that would just mean f prime of t is equal to 3t squared. And with that, that is going through that process to go from our actual f of t to f prime of t when the integral is actually inside the function. We got another example of that for you. This one is f of t equals the integral from 1 to t of 4x cubed minus 2x dx. So we're just going to do the same thing. If we actually evaluate this integral, so integrate 4x cubed, we'll get x to the fourth. And if we integrate negative 2x, we'll get minus x squared. Now remember, we have to actually plug in our bounds. So if we plug in t, we will get t to the fourth minus t squared. And remember, you have to subtract plugging in your lower bound. So 1 to the fourth would be 1. 1 to the fourth is just 1. And then subtract 1 squared is also just 1. And so we'll be left with t to the fourth minus t squared. That stays. And then we have to subtract 1 minus 1. But 1 minus 1 is just 0, so this is all just 0. So we're just left with t to the fourth minus t squared. And this is still our f of t, because all we did was evaluate the integral. So now if we actually differentiate, we'll get f prime of t equals 4t cubed minus 2t. And yeah, that is our derivative for that one. Okay, we have one that looks slightly different here. This one says f of t equals the integral from t to t squared of cosine of x dx. So there's two different things here. One is that it's trig, which shouldn't be an issue. It's just another kind of integral. We know how to integrate cosine x. But the main different thing is that both of the things in the bounds here, both of these are variables. None of them are numbers this time. So let's just continue, see how it plays out. It should be the same, but we'll find out. So remember, we just integrate. So if we integrate integrate cosine x, we will get sine x. And then we have to plug in our bounds, so from t to t squared. So plugging in t squared, we will get sine of t squared. and subtracting in our lower bound, that will just be minus sine of t. I'm going to rewrite that. That was not great handwriting. But yeah, that is all it is for f of t. And now we have to actually take the derivative. So f prime of t equals, now here be careful, notice that if for sine of t squared, this is actually going to be chain rule this time. So if you remember chain rule, the derivative of sine t squared will give us cosine of t squared multiplied by 2t. And then we can just subtract doing this one. Derivative of sine t, that is not chain rule, that's just normal trig. So that will be minus cosine of t. And with that, that is our derivative. So there's more terms in our answer this time. Or there's not more terms, but there's more stuff going on in this first term than when we were just integrating, where one of the bounds was a number and one of the bounds was a variable. So when they're both variables, it looks like more stuff happens. So it looks like it's just a bit different, but it should work out fine. So the thing that we really want to do is we want a really easy way to go from f of t to f prime of t when f of t has an integral in it. And it's not exactly clear what our formula would be, because it's just a lot going on. It's like the first two looked kind of simple, but then that third example I showed you, there was more stuff going on, like when both the bounds are variables. So it looks a bit more confusing, so I'm just going to give you the formula rather than walk through and try to discover it. So what it would be is, let's say f of t is our function, and that would be equal to the integral from g of t to w of t of h of x dx. No, it's a lot of notation, but it's just showing that all of these things are their own function. Well, that'll be important when we actually take the derivative. So f prime of t would be h of w of t times w prime of t minus h of g of t times g prime of t. And so that also is a lot, so I'm going to say what all this means in terms of words and not just a bunch of notation. So basically what we do is we take this inside function of the integral, whatever is inside, we're going to first plug in the top bound. That's what this h of w of t part is. And then what we have to do is this term we just got, we have to multiply it by the derivative of the top bound. Next what we do is we have to subtract, and then we're going to do the same thing with the lower bound. So plug in the lower bound to our with the function inside the integral. That's what this h of g of t part is. And then multiply by the derivative of the lower bound, which is this g prime of t part. So this is the formula that we use to actually differentiate an integral, whatever, or yeah, stuff. That's our formula we use for it. And then so I'm just going to shrink this formula down, write it up at the top of the board, and we're going to go through a few examples with this. Alright, so these next few examples, all we're going to be doing is going straight from our function to our derivative using the formula I just showed you. So this first example is g of x equals the integral from pi to x of cosine t. So using the formula, what it says is we first have to take this function that inside the integral, and we're going to plug in the top bound. So the top bound is x, so we're just going to be left with cosine of x. Then we have to multiply by the derivative of the top bound. So the derivative of x is just 1, so just multiply by 1. Next we have to subtract, plugging in the lower bound, so cosine of pi. And then we have to multiply by the derivative of the lower bound. And remember, pi is just a constant, so the derivative of any constant is going to be 0. And then so if we want to simplify this, this is 0 times cosine of pi. 0 times anything is 0, so that goes bye-bye. So we are just going to be left with cosine x times 1, which is just cosine x. So that means g prime of x will simply equal cosine of x. Alright, our next one here is that, so we're given f of t equals the integral from negative 4 to t of 1 over x plus e to the x minus x cubed plus 3x. So there's a lot going on there, but remember, we don't have to differentiate or integrate any of the stuff inside here. We just have our formula, which is plugging in the bounds and differentiating the bounds, so it's not going to be that bad. So remember, the first thing we do is we plug in the top bound to all our stuff here. So that will give us 1 over t plus e to the t minus t cubed and plus 3t. Next, we have to multiply all this by the derivative of the top bound, and that's derivative of t, which is just going to be 1. Next, we will have to subtract, and we will plug in this lower bound, which is negative 4. So 1 over negative 4 plus e to the negative 4 minus negative 4 cubed and plus 3 times negative 4. And with that, we will also have to multiply this whole next term by the derivative of the bottom bound. The bottom bound is negative 4, which is a constant, so derivative of that will be 0. And because all of this is multiplied by 0, this all goes bye-bye. And that means we just have this, and it's all multiplied by 1, so it's basically exactly what it is. You don't really need to simplify, but I'm just going to get rid of the brackets. So that means our derivative is just equal to 1 over t plus e to the t minus t cubed plus 3t. Okay, our next integral we have here is f of x equals the integral from 2 to x of 4t cubed minus ln of t dt. So again, all we're going to do is just take the derivative using our formula. So first we plug in our top bound, so that will give us 4x cubed minus ln x. And then we have to multiply this term by the derivative of the top bound, so derivative of x will just be 1. Now we subtract, plugging in the lower bound, which is 2, so that will give us 4 times 2 cubed minus ln of 2. And then lastly, we have to multiply this second term over here by the derivative of the bottom bound. 2 again is also a constant, so derivative of a constant is 0. And if we simplify, 0 times anything is 0, so all that goes bye-bye. And that means we just have all this multiplied by 1. So simplifying will just be 4x cubed minus ln of x. And that will be our derivative for this one. Okay, our next step, we have g of t equals the integral from 0 to t cubed of sine of x squared. And then, so now we have to take the derivative of g of t. So, remember, to do that, we're going to first just plug in the top bound to our function inside the integral. So that will be sine of t cubed squared. That's because the x is squared, so that means our t cubed is going to be squared. And then we have to multiply by the derivative of the top bound. And this time it's actually going to be something other than 1. The derivative of t cubed will give us 3t squared. And now we subtract, plugging in our lower bound, which is 0. So that will be sine of 0 squared. And then we have to multiply by the derivative of the bottom. Derivative of 0 is still just going to be 0. And so if we simplify, all of this again is still multiplied by 0, so that goes away. And over here we do actually have some simplifying. We can move this 3t squared to the front. And inside the integral, or not the integral, inside the sine function, we have t cubed squared, which is the same thing as just t to the power of 6. And now with that, that is our integral. Yeah. Okay, this next one is just basically to show you that don't be scared, no matter what your bounds are. As long as you can take the derivative, it's fine. Even though we have a trig function in our bounds, which is really abnormal, that's completely fine. We know how to differentiate secant, so it'll be fine. So, remember the first thing we do, as always, is just plug in the top bound to our equation. So that will give us 7 to the power of secant t plus 7 over secant t. Now we have to multiply by the derivative of the top bound. So the derivative of secant t will give us secant t times tangent of t. Now again, we subtract, plugging in the lower bound, which is 7. So 7 to the 7th plus 7 over 7. And then we multiply by the derivative of the lower bound. So derivative of 7 is constant, so it's just going to be 0. So all that times 0. And as before, all of that stuff goes bye-bye, because 0 times something, anything is 0. And over here we have some simplifying to do. We don't really have to bring this secant t, tangent t to the front, nor do we have to distribute. All we really have to do to simplify is that first term. I'm just going to rewrite the secant t, tangent t first. The first term, 7 to the secant t, we can leave that just as it is. But if you want to simplify, 7 over secant t is the same thing as 7 cosine of t. And that's because secant t equals 1 over cosine. So 7 over 1 over cosine is just the same as 7 times cosine. And with that, that is that problem. Okay, this next one is one where we actually have both of our bounds with variables in them. But again, it's the same thing as normal. Just follow the formula. So First thing we do is we plug in our top bound to all the stuff inside the integral. So this will give us 5t times e to the 5t squared plus 5t. And then derivative of the top bound, which is 5, so multiply all of that by 5. And subtract, plug in the lower bound to everything. So 2t times e to the 2t squared plus 2t. And then multiply all that by the derivative of the lower bound, which is just going to be 2. And then now, pretty much there isn't too much we can really simplify here. We can distribute this 5 in, that will give us 25t e to this power. We could simplify this 5t squared, that will give us 25t squared plus 5t. Then we can do the same thing over here on the right side. Distribute that 2 in, we will get 4 times 2. E to this 2t squared we can simplify, so 4t squared plus 2t. And pretty much that's about it. Yeah. The only difference from all the other ones we did is both of the bounds actually had derivatives other than 1 or 0, but it's still the same exact process, just following the formula. Before we move on to something slightly different, this is our last one, and this one is a bit wonky. We have a function and a variable in our bounds, but again, just follow the formula. So, f prime of x equals, or not, f prime does not equal the integral, I don't know why I wrote that. F prime of x, we have to first plug in our top bound. So plugging in our top bound here, that would give us x squared over x squared cubed plus x squared. And now times the derivative of the top bound, so the derivative of x squared will be 2x. And subtract, plugging in the bottom bound, which is tangent x. So this will give us tan x squared over tan x cubed plus tan x. And then you have to remember, multiply by the derivative of the bottom bound, which is, so derivative of tangent will give us secant squared x. And this one's just a bunch of random terms. There's nothing really to simplify here. We could turn x squared into x to the 4th, x squared cubed to x to the 6th. We could distribute this 2x in here, so that would give us 2x to the 5th now. That's our first term. Over here, there really isn't anything you can do. If you want to do anything, just put this secant squared in the numerator. So tangent squared x, secant squared x, over tangent cubed x, plus tan x. And that one, that's it for that one. Okay, a very similar thing that we might see is not only will the problem want us to find the first derivative, but they might also want us to find the second derivative. So for these next two examples, we're going to be finding both the first and second derivative of this function containing an integral. So we can begin by just doing it like we normally do. Use this formula, and so we can take the derivative of the function. So f prime of x will equal, we have to plug in the top bound, so plug in x to all of these. We will get 3x squared minus 8x plus 7. Then again, we multiply by the derivative of the top bound. Derivative of x is just 1. And then we subtract, plug in the lower bound, which will be 3 times 0 squared minus 8 times 0 plus 7. And multiply by the derivative of the lower bound. Derivative of 0 is just 0, so we will get 0. As many times before, all of this stuff on the end goes bye-bye because we're just multiplying by 0. And we are just left with that f prime of x equals 3x squared minus 8x plus 7. And now, this would be our first derivative, but like I said before, we want to find also the second derivative this time. And so, it's going to be nothing crazy special. We're just going to take the derivative again, like we've always done, differentiating functions. So, derivative of 3x squared is 6x, derivative of minus 8x is minus 8, and derivative of plus 7 is just 0. And so with that, that's our first derivative, and that's our second derivative. So with this kind of problem, when we want to find both the first and second derivative, we have to use the formula for this first derivative when we're deriving the definite integral, and then the second one is really easy. We just do normal differentiation rules. Sometimes you might see problems like this where they actually use just like g of t or some kind of just notation of a function like that inside the integral, and that's more so to test your understanding of the topic. So let's go through this one. This one, we again want to find the first and second derivative, so we just follow the formula. We will find f prime of x equals, plug in the first bound, so plugging in the first, or plugging in x to g of t, we will get g of x. And then we have to multiply by the derivative of the top bound, which derivative of x is just 1. Then we subtract, plugging in the lower bound, so that will be g of 1. And then multiply by the derivative of the lower bound again, and so derivative of 1 will just be 0. And so this g of 1 times 0 goes bye-bye. It's multiplying by 0. So we're just left with that f prime of x equals g of x. And from here, we could take our second derivative. We'll find that f double prime of x equals g prime of x. And so this is a general kind of thing. If a function equals a definite integral, that means it's, or let me rephrase that. If a function equals a definite integral of another function, that means that the first function's derivative will equal the second function, and likewise, the first function's second derivative will equal the second function's normal first derivative. So that's what we learned from going through this kind of thing. And with that, we've pretty much wrapped up going over differentiating an integral. And so now we are going to move on to average value. All right, now before we start talking about finding average value of a function using integrals, let's just take a step back. How would we want to find the average value of a set of numbers? Like say we were given 1, 2, and 3. How would we find the average value of that? And the answer is, what we would do is we would add the terms together and then divide by the amount of terms. This is something we learned a long time ago, like I think we called it mean or something like that a while back. So basically, like I said, we add all the terms together, so 1 plus 2 plus 3, and then divide by the amount of terms. And here we have 3 terms, so we divide by 3. If we simplify this, we would get 6 over 3, which is just going to give us 2 as our answer. And so we can actually use this concept to create a formula using integrals. So if you remember in lesson 4.3, we learned that in a definite integral, specifically, like integral from a to b f of x dx, this can actually be rewritten in another way. And it could be rewritten using sums. And so if it can be rewritten using sums, and sums are just summing a bunch of numbers together, that's really similar, pretty much the same thing as this top half of our normal average formula here. And so that's why when we're rewriting this formula we have using integrals, the top half is just going to be the integral from a to b of f of x dx. But remember, that just accounts for the top half where we're adding all the terms together. We then have to divide by the amount of terms. And to do that, that is going to be where we divide by b minus a. Because b minus a gives us our terms of the interval, whatever. And so, this formula looks a little sloppy, so I'm going to write it more formally for you now. So the formal way we see the formula is that if we want to find the average value of f of x on the interval a to b, we would use the formula 1 over b minus a multiplied by the integral a to b of f of x dx. And so this is the formal way to write our average value formula. And so I'm going to rewrite this, and we're going to go through a few examples of actually using this formula. Alright, so for the rest of the problems of this video, all we're going to be doing is we're going to be finding the average value of the function given to us with the interval given to us, and we're just going to be using the formula that we just found. So, in order to do that, the first part of the formula says we have to do 1 over b minus a, which essentially means 1 over the high bound of the interval minus the low bound of the interval. So for us, that would be 1 over 4 minus 0. Then we multiply this by the integral from the low bound to the high bound, so from 0 to 4. And then we would write, on the inside, we would write f of x. And so we could write all of this stuff inside here and then dx, but we don't have to. What we could do is just write f of x and then dx. The reason for this is, one, we're provided with f of x, so we could just rewrite f of x here, and it's fine. And the second reason is that for average value problems, most of the time it's calculator active. So we could just write this as our work and then actually plug this into the calculator. When we plug it in, we will write all this stuff. And then it just saves writing time on your work, and it still gets the essential point across. And so if we were to plug this into our calculator and solve it normally, that would give us an answer of, where was it? An answer of 23. Yes. And that's our answer for that one. This next one's a really good example of why we just want to write f of x inside the integral rather than actually writing it all out. And so here we have f of x equals x squared minus 5x plus 6 times cosine of pi x from the interval to -1 to 5 over 2. It's just a lot of stuff, so it's a lot easier to just write f of x. So let's go through the process. First, we need our 1 over b minus a. So for our case right now, that would be 1 over 5 over 2 minus a -1, so essentially plus 1. Then it will be times the integral from -1 to 5 over 2. And then it will all just be of f of x dx. And then we leave it at that. Yes, this kind of looks ugly over here because we have that fraction inside of a fraction or whatever, but we're just plugging it into our calculator so we don't have to worry. And this one will actually give us a decimal this time. Our answer will be -1.620. Remember, we want to go to 3 decimal places, but yeah, that's our answer. Okay, this next one, still going to do the same exact idea. We have f of x equals sine of 2x multiplied by e to the power of 1 minus cosine of 2x. And our integral is -pi to pi. So starting off for our formula, our 1 over b minus a will be 1 over pi minus a negative pi, which is essentially saying 1 over pi plus pi, so we'll get 1 over 2 pi. Then our integral will be from a to b, so we'll have from -pi to pi. And then on the inside, we could just write f of x and dx. And then at this point, we just plug it into our calculator, and we would actually get an answer of just 0, which really nice to get something as ugly as this integral to actually simplify down to like this. All right, our last 2 problems today are word problems. So again, I'm just going to put them on the screen through editing. So the first one says that the approximate number of bacteria in a sample virus is given by b of t equals 327 times 4/5 to the power of -t, where t is time in minutes. What is an approximation for the average number of bacteria in the sample between 5 and 20 minutes? So the hint that we're going to be using our average value thing is, one, it says the average number of bacteria in the problem, and also the fact that it says it's going to be between 5 and 20 minutes. That's an interval. So if we were actually writing down what the information they're giving us is, as I said, they did give us an interval from 5 to 20. And we want to find the average value of b of t, which they said was equal to 327 times 4/5 to the power of -t. So we can now use our actual formula because we have our function to integrate and we have our interval. So the formula first said to do 1 over b minus a, so 1 over 20 minus 5, multiplied by the integral from a to b, so from 5 to 20, and then of just the function, so of b of t dt. And from here, this is all the work we need to show, as I said before, so we can just plug this into our calculator, and from that we get our answer is going to be 8,175.4, or no, not 0.4, 0.545. And then if we wanted to use units, because it's a word problem, it would be this much bacteria. And that would be our answer. This next one's really similar. We're just going to have to be a little bit more careful with our actual interval. So this one says the rate of which water is pumped into the tank is modeled by W of t equals 2,000 e to the -t squared over 20. So I'm going to write that real quick. W of t equals 2,000 e to the -t squared over 20. This is our function that we're going to use. So let's move on and see if we could find our interval. It says that this function is measured in liters per hour, where t is measured in hours after 10 a.m. So find the average rate of what water is pumped into the pipe between 10 a.m. and 6 p.m. So the issue here is we are not going to do an interval of 10 to 6. Even though it says 10 p.m. or 10 a.m. to 6 p.m., that's not correct. It says our variable t is modeled in hours after 10 a.m. So because of that, because it's the hours after 10 a.m., we are going to assume that 10 a.m. is times 0. So our interval starts at 0. And they wanted to go from 10 a.m. to 6 p.m. So the amount of hours between 10 a.m. and 6 p.m. is actually going to be 8 hours. Because from 10 a.m. to 12 p.m., that's 2 hours. And then 12 to 6, that's 6 hours. So 2 plus 6 is 8. So that's where we actually get our interval. And so once we have this, we can actually use our formula again. So 1 over b minus a, in this case, would give us 1 over 8 minus 0, times the integral from 0 to 8, and then just of w of t, dt. And from there, we can actually just go straight to our answer by plugging it into our calculator, and we will get an answer of 979.524. And then in terms of units, it's asking for the average rate at which water is pumped into the tank. So this is going to be, what was it? It's going to be liters per hour. And that would be our answer for that one. And that pretty much wraps up our lesson. So, yeah.